Understanding physics, uncertainty. This is very important. There'll always be questions about uncertainty in the A-level exam. So in this video, what does uncertainty mean? Different ways of estimating the uncertainty in measurements, how we combine uncertainties when we calculate quantities from our measurements, and how we might go about minimizing uncertainty in our experiments. So imagine you drop a ball, you hold a ball and you let go of it, and you use a stopwatch to time how long it takes to hit the floor, and you get a time of 0.45 seconds. Now, is this the true value? The true value is how long it actually took, and basically, is your measurement equal to the true value? Well, what do you think? I mean, one thing you could do is do it 10 times. And if we do it 10 times, we might get a set of data, a data set that looks like this. We might get lots of different answers. Okay? Now, can we get the true value from this data? And the answer is probably not. Now, why? Well, one thing is that we're assuming that the ball will take exactly the same amount of time to fall. It probably won't. Another factor is that the true value will be an irrational number. You know, it'll go on forever. There'll be an infinite number of digits. So you can't write it down. All we can really say is we can say what the average is of our data set, the average of our measurements is, and we can say what the upper and lower limits are. You know, we can say that the average is about this and it's between this and this. Okay? And this is what we mean by uncertainty. The time it takes to fall is 0.43 plus or minus 0.04 seconds. The mean value is what we do is we ignore outliers. And you may have noticed looking at the data set there was an obvious outlier. We ignore that when we work out our mean. And then we have what we call the absolute uncertainty. And what we can do is work out the percentage uncertainty. If we do 0.04 divided by 0.43 and then times 100, we get 9%. So there's the absolute uncertainty and the percentage uncertainty. How do we go about finding the uncertainty? Well, there's different ways that we can estimate it. What we could do is do this, if we had our 10 readings, is do what we call a dot plot. And if we do a dot plot, we can clearly see that one of the readings is an outlier. In fact, this is what we would call a blunder. I reckon somebody wrote down the reading wrong. Okay? So looking at the other results, we get something which looks like a normal distribution. That hump shape, you should get something like a normal distribution. And then if we put the mean on this dot plot, and then the range would be twice the uncertainty. A few notes: we can only ever estimate the uncertainty. We can't say what it is. You should only give the uncertainty to one significant figure. You say it's 9% or 8% or 10%, not 10.4%. You know, how can you be that certain about the uncertainty? It should just be one significant figure, and you should be generous in your estimate. There are statistical ways of getting the uncertainty. There's something called the standard deviation, but this goes beyond us. If you're doing A-level maths, you'll do standard deviation, but we're not bothered. Another way of estimating the uncertainty is if we consider the resolution of our measuring device. And the resolution is all to do with the smallest scale division. If we're using a normal classroom ruler, then that has a resolution of 1 millimeter, 0.1 centimeters, whereas a micrometer has a resolution of 1/100 of a millimeter. A kind of general rule of thumb is that our uncertainty is equal to half the smallest scale division. So if the smallest scale division is a millimetre, then our resolution is half a millimetre. Sorry, our uncertainty is half a millimetre. Combining uncertainties. Now, sometimes we calculate a quantity from our measurements, and when we do that, we often have to combine uncertainties. For example, if we measure the diameter of a wire, and let's say we get a value of 0.24 plus or minus 0.01 millimetres. First of all, what's the percentage uncertainty? And if we work out the cross-sectional area of this wire, what will be the uncertainty in that? Well, the rule is that if we multiply or divide uncertainties, then the resultant uncertainty is the sum. Okay, whether you're multiplying or dividing, you add together the uncertainties. For example, if the uncertainty in the diameter is 4%, then the uncertainty in the area will be 8%, because we're squaring it, so it's 4 times, well, the diameter times diameter, or radius times radius. So we add together the 4% and we get 8% for the area. Here's another example. The resistance of a component is measured by measuring voltage and current. The voltage is 2 plus or minus 0.05 volts. The current 0.15 plus or minus 0.01 amps. What's the percentage uncertainty in those? Calculate the resistance of the component, stating the uncertainty in the value you give. Well, the uncertainty in the voltage is 3%, I am saying. It's actually 2.5, but I'm giving it to one significant figure. I'm saying it's 3%. The uncertainty in the current is 7%. The resistance is the voltage divided by the current, so the uncertainty in the resistance is 10%. Remember that we add them together. So 3% plus 7% is 10%. When we design experiments, we should make an effort to minimize uncertainty. You'll never get rid of uncertainty, but you can make an effort to minimize it. And one way is careful choice of measuring instruments. In the last example, which voltmeter do you think would be the best one to use? Which one has the best resolution? Okay, which one would be most suitable for measuring a voltage of about 2 volts? And really, to be honest, I just use multimeters all the time. If I've got them, they've got very, very good resolution and they're very, very versatile. When we design experiments, we should always take repeat readings. Why do we take repeat readings? Well, that means that our average value will be more reliable because it's based on more data. It will help us to identify any anomalous readings, any outliers that we should ignore. If we don't ignore any anomalous readings, it will minimize their effect. The more readings we take, then the less they will affect the average if we don't spot them. And it will help us to estimate the uncertainty. You know, if we've taken several readings, then we can use our readings to estimate the uncertainty from the maximum and minimum values. We should choose equipment and methods that will minimize uncertainty so that we're avoiding systematic errors. And again, to minimize the effect of random errors. I'm going to do another video all about errors.